Alright, hell yeah, let's do it. So a commenter's like, hey, can you do one of these problems where you have two blocks that are stacked up and we got friction? And so it's kind of cool because I kind of know of a way to simplify this thing kind of right off the bat. Like, how do you take something weird or complex, kind of make it simple? So they're saying that this floor is frictionless, you know what I mean? And so even that is just, what does that mean? Like, it's an icy floor? Does that mean it's not going to take any force? You know, I kind of like to ask those questions that are, like, obviously it's going to take some force to move. You know, if we just have one block on an icy floor and I want to move it, you know, it's still going to take a force to start to move it. But the cool thing about a frictionless floor, whether it's just like you know, one of those roller surfaces to like transport like UPS boxes, or if it's an ice skating rink, the second you put like a puck into motion, it just keeps that velocity. So that's pretty cool. You apply a force, you get a speed, but then it just maintains that speed. But it does take a force to, so F equals ma, kind of the fundamentals of Newtonian mechanics, is if I have a mass, doesn't matter where it is in the universe, if I want to, and it has a velocity of 0, and I want to move that mass, I want to change its velocity, I definitely need to apply a force based on this. If I apply a force, I have a mass, it's going to accelerate, we're going to get a number on that, and that number of acceleration is going to be change in velocity, change in time. Okay, sweet. Now, block A and block B, in between this, we have a friction force. And it has a coefficient of kinetic friction of 0.5. And, I'm sorry, it has a coefficient of friction of 0.5 with a kinetic friction. So this is going to be your static friction. This is your kinetic friction. Okay, so sweet. So I was just like, well, I think one of the simplest ways to make this problem simpler is to have your floor here. I'm just going to say, hey, this is block A. But guess what? Let's link it up, you know what I mean, with little eye bolts, a little carabiner, another eye bolt, and now we're going to put block B right here. And now we're going to apply a force. And now the question is, let's see, and the force is going to be 100 newtons. So in this scenario, let's solve this one first. This is the easier problem. I mean, this gives you like the ballpark, because what's it asking? It says the acceleration of block A. It wants to know the acceleration of block A. Well, cool. We're pulling on block B. Obviously, if this problem is set up well, block B won't be rigidly attached. We'll apply more friction here than block B can, like the friction force can withstand. So, and if the coefficient of friction is 1, then if I apply, and this has a weight of 7, well, I mean, it has a mass of 7 kilograms, but we know the gravity is 10 meters per second. So the weight of this is going to be mg, so that would be 70. So if we apply a force of 70 and the coefficient of friction is 1, hell yeah, these things are just going to be rigidly attached together, and we're going to have motion. So that's kind of like this. So this scenario, this simple scenario, is if mu is 1, and then the force applied would be 70 newtons. But if we apply 100 newtons, well, you would have to, you know what I mean, the normal force down, the force of friction that's kind of withstanding, force of, I'll just call it little f, that force of friction is going to be mu times the normal force. So if we're saying that this is 100 newtons, and then the normal force is just 70. What is mu? That would be solving for this coefficient of static friction. That would be 100 divided by 70. Alright, sweet. So 100 divided by 50 would be 2. 100 divided by 100 is 1. So we're somewhere in between. Anyway, I'm really bad at dividing fractions like this. The inverse would be 0.7, so what's the inverse of... I have no idea. So 100 divided by 70. I don't even know how to guess this. You know, you could... These are really difficult. Like, hey, like 10 divided by 7. Well, or is it difficult? You know what I mean? Is 10 divided by 7 hard? I don't know. Because 14 divided by 7, maybe that's the better way to look at it. 14 divided by 7 is 2. 7 divided by 7 is 1. So does this mean it's going to be less than 1.5? You know what I mean? I'm just going to guess 1.45. And I feel like I'm going to be wrong. I feel like it's not a linear relationship. Hey, I was pretty close, 1.42. So at least we're improving our mental math guessing skills. It's always a good thing to do. All right, so yeah, if this coefficient of status friction was 1.4, yeah, we would just pull on this block. It would be like literally glued to block A. And but we still, in that scenario, if these two blocks are connected, we still want to find the acceleration. That kind of hooks us in to be like, that would be the most acceleration of the system. Because, man, this is so interesting. Yep. Well, yeah, let's do this, but yeah, it's just kind of bizarre that if block B moves, you still are applying a little force to block A, and it's the frictional, it's the component of the frictional force. That's the component that you're applying. And, oh, it's so fascinating. And if this, so what you identify is if this force of 100 newtons is greater than the coefficient of static friction, which it is, it would only take, because this mg is going to be 70 newtons, we have a weight of 70 newtons, and this mu is 0.5, it's only going to take 35 newtons, of force to make this thing start sliding and moving. And then if it started sliding and moving, the coefficient of kinetic friction of 0.4, mu times the normal force, or 0.4 times 70, which is 0.4 times 70, 28. All right, hell yeah. So that would be 28 newtons. So sweet. So of that 28 newtons, so you can only have 28 newtons that's resisting whatever 100 newton force here. But because you do have this force of kinetic friction that's like always applying 28 newtons. So yeah, this is interesting because like, let's say your objective is just to move block B. You don't even want to move block A. And if you move... Oh, this is bizarre. And then, because one thing that you, from an energy perspective, is, let's say block A isn't on a frictional surface. Like, it's rigidly mounted to the ground. And then you start to move block B. So this kinetic friction applies. Well, that means that the kinetic friction is like fighting back your 100. So you're theoretically not pulling this block with that perfect 100 newtons. You're losing 28 newtons due to like all that grippiness. And typically what we say for that grippiness of friction, that the energy goes into heat. Like, that's kind of one way to look at it. I don't like to look at it like that. I like to look at friction like this. I like to look at friction that it's like a bunch of springs that are kind of like hooked. So you have a bunch of springs that are kind of hooked like Velcro. And maybe they're kind of hooked the other way. And when you have something that slides across them, this thing also has springs that are hooked like Velcro. And when you actually start to move this kinetically, these springs can go from their original length to a maximum length, and then they kind of stop, they kind of break away. You know what I mean? So you kind of have, you're having this kind of breakaway motion, and this spring's maybe attached to that spring. But at the same time this spring breaks away, like a new spring is being like, oh hell yeah, like we're doing it, we're hooked together now. So I think this is actually a I'm just going to be narcissistic and say that, yeah, I think this is exactly what's happening. And sure, you're going to get motion of small particles down to like molecular levels that are going to cause vibration, that are going to cause heat, excitation, you know what I mean, whatever. But when it comes down to it, I think the force of friction is pulling springs until they pop, but then you're re-engaging new springs, and it's a consistent manner. That's why kind of coefficient of kinetic friction is always, it's pretty consistent. Like I think like the second you go from static to kinetic, I think you have like a weird little like non-linear drop. But then once from you know, just, and even at slow speeds, if you're moving at hella slow speeds, but anyway, I think from normal speeds to like even fast speeds, that's going to be pretty plateaued. It's going to be 0.4. Now at really high speeds, yeah, maybe that reduces at really high speeds, and you know, and then it'll go up at slow speeds to 0. Okay, booyah. But it's these constant interactions of like the frictional molecules that are gripping and stretching and kind of, you know, doing their thing. I think that's a good representation. So that's why if this thing's moving, you're not pulling with 100. I mean, you're pulling with 100 newtons, but like if we're talking a mass, if this mass is in outer space and we're pulling with 100 newtons, and this has a mass of 7 kilograms, booyah, F equals ma. Rearrange, A is F over m, so we would have 100 divided by 7. So we would have an acceleration of 14 meters per second squared. Change in velocity. Every second, this thing's going to change in velocity by 14 meters per second. But we don't have that. We don't have that 100 force operating or pulling on a 7 kilogram mass. We only have a component of it because we're losing some to friction, and we're losing 28 newtons to kinetic friction. And so it's 100 minus 28, and we have 72 newtons left. So this equation, so 72 newtons, and we have 7 kilograms acceleration, would be a force of 72 newtons. And then we would have 7 kilograms, and booyah, 72 divided by 7. I don't want to get the answer right off the bat, and it looks like we're not. And why are we not getting the answer? Because this is the acceleration of block A. So hell yeah, block B kinetically will move at a speed of a change in velocity of 10.2 meters per second every 1 second. You know, acceleration. All right, so but now because that's the case, this 28 newtons, this force of friction, is what is actually being applied to block A. So block A has a 28 newtons force, and its mass is 35 kilograms, and we got 28 divided by 35. Again, acceleration is force over mass because F equals ma, and we just rearranged for acceleration. All we did was take the m downstairs, but even that, I think that can get some students. I don't want to rearrange F equals ma. I don't even know it's an equation that actually works. But anyway, so we have 28 divided by 35, and we get 0.8. So obviously that's an answer, but we're going to try to double check this just to make sure we're of sound mind and we're doing things right. All right, booyah. So let's go back to this example, and we're going to have 100 newtons operating on 7 plus 35, on 42 kilograms. And so F equals ma. We want to know the acceleration. acceleration is force over mass, we would have 100 newtons, in this case, divided by 42 kilograms, 100 divided by 42. So this whole system has a potential, if it's locked together, has a potential to move at 2.38 meters per second squared, an acceleration of 2.38. We see that if block B reaches kinetic friction, or let's say there is no friction between these, that's the other one. If block B is just able to move on a frictionless surface, we're pulling 100 newtons on a 7 kilogram block. Again, F equals ma. We rearrange for A, the acceleration is force divided by mass. So we take that 100 divided by 7, and we would have an acceleration of 14.3 meters per second squared. So hell yeah, if we have this 100 just operating on B, we're going to move that B real fast. But if it's connected to both because of the sticky friction between these, it could be slowed at like 2.38. But now we get kind of this mix because B is able to move, but there is imparting some kinetic friction, and that grippiness of that kinetic friction is reducing this 100 newtons, and it's increasing, and it's being applied to block A. Now, man, I struggle with the free body diagram, so I think I'm going to end this video with trying to draw the free body diagrams. It's bizarre because I just did a problem the other day, and we're going to talk about this because it's so interesting. Like, if you want to take a step forward, you got to push the Earth back. Like, at the same amount that you're pushing forward, like, you're taking your mass and getting it to go forward. You're at a stopped position. Your velocity is 0, but in the process of taking a step, you're reaching a change in velocity. So at the halfway point of taking a step, you went from 0 velocity to a max velocity, and to do that, you had to apply a force to the Earth, and that actually pushed the Earth backwards at the same amount that you're being pushed forward. And so that's going to be the conservation of momentum. And so we're going to take a look at that. And hell yeah. And I got this kind of more down. In the last video I drew, I kind of went on a limb. And I was saying that if you have a Earth that's like a thin shell, where all the mass is on the outside, and it's kind of like an Einstein's dream Earth, where you're actually like crawling your way along it, feet and but anyway, I guess you're a dog, but anyway, so this dog is crawling away along this planet, and as it does so, the planet is rotating that way. And so what I mentioned in the video is, like, let's say this planet has the mass, the mass of this planet is the same as the mass of the dog. And so, but that's still, a planet is a spherical thing. And so but I thought of a scenario that will work. So let's say you have to do this a lot in physics, and it's mentally challenging. We're going to take a massless hoop. So it's not a sphere, it's a massless hoop. It has a center, and then from the center, and it has a fixed center point, and then you have a massless rod connected to the massless hoop, and on the connected to the hoop, right at the end, is a chunk of mass. All right, so hell yeah. So you have this chunk of mass right here that is the same mass in kilograms as our dog, and hell yeah. And so as the dog, starting from 0 velocity, takes a step forward, you know what I mean? Because you can't do these problems in terms of constant velocity. You're going from 0 velocity, the dog takes a step forward, and let's say in that process, it's moving at center of mass 1 meter per second. So in the process of taking that first step, it gets up to 1 meter per second, and that is the only slice of reality we're interested in. We're not even worried about that dog taking that, landing that step. We're just saying everything's stationary. Velocity of the planet is stationary, velocity of the dog, but the dog does move at center of mass 1 meter per second gets it up to top speed, and it does that in a process of time of 1 second. Alright, booyah. So if the dog starts with 0 velocity and gets up to 1 meter per second, its top speed in 1 second, what's its average velocity? Well, that's going to be 0.5 meters. So it's really good to be able to do at least that when we're talking about kinematics. Being like, okay, I'm starting at 0 velocity. In 1 second, I get up to a speed of 1 meter per second. What was my average speed? Well, it's just going to be the difference between these speeds. 0 meters per second to 1 meter per second. Alright, sweet. And in here we have an acceleration because our acceleration is change in velocity. We did 1 meter per second in 1 second. So 1 meter per second squared is our acceleration in this imaginary problem. Okay, so this dog travels a distance forward, and we're going to say this planet is hella tiny. So a half a meter is right there. 1 meter is right there. So cool. So we travel forward half a meter. So so what happens to the mass? The mass actually goes this way a half a meter. So now the mass is over here, and now the dog is over here. Dog's at a half a meter, the mass is over here at a half. And why is that? Like this is such the underrated, it's in the physics book that I have, it's just like, for sure, it talks about momentum of rockets. And the rocket has fuel that gets, shot out the back. And if a rocket is just in space, it's full of mass of fuel, and at mass of the rocket shell. Maybe the center of mass is right in between. But the second, like, hey, you do like a 5-second burn, and all these mass particles have a velocity this way. Well, your center of mass, I mean, if this thing just has literally 0 velocity, like you just stick it into space, and then fire up the boosters. It's just floating there in space, fire up the rockets. This center of mass won't change. The rocket will go this way, but the rocket... and then all those molecules, they're going to go this way. And this rocket is infinitely going to go that way forever. And these molecules will also go infinitely that way forever. They'll be going hella fast. This rocket will be going hella slow. But the center of mass will stay the same. It's very fascinating. And so in this scenario, we developed a scenario where the mass of this planet is the mass of the dog. And the mass is all centered right underneath the dog on a frictionless hoop. So the planet is a 2D. On a frictionless rod towards a center point of this, pivot point. It's pinned to the universe. And this dog takes that step forward. As it changes its momentum, it goes from 0 to 1 meter per second. The planet also goes the other direction the same amount. And so we can do this same thing and make it a little bit more representative. Instead of we're still going to do a 2D planet. It's going to be shaped as a disc now. We still have a center point, maybe as a spoked wheel. So we have massless spokes out to a ring of mass. And we're going to say like, this has 100 little chunks. And I wouldn't do 100 to start. I would be like, hey, let's do a ring where you have like 2 chunks, 2 chunks of mass on the massless thing, and now your dog moves forward 5 meters, and these 2 chunks still weigh, I don't know, yeah, I was going to where the 2 chunks still weigh the mass of the dog, right at the beginning, and the dog goes 5 meters forward. Still, these two half chunks still go 5 meters, you know what I mean? Because if we have a half of a mass going 5 meters, 2 half masses going 5 meters, that's the equivalent of just, 1 chunk of mass going 5 meters, right? So visually you can see that. And the dog is the 1 chunk of mass going 5, and then these are the planets going in the opposite direction 5 meters. So then you can have a hoop with unlimited amount of, you're going to have little chunks of mass like along the perimeter, but we're still going to say this whole planet is the mass of our dog. Okay? And then we still have the dog on top, and the dog is still going to go that 0.5 meters, take just one huge step, or just, it's a step, it's moving at center mass 0.5 meters, it's not too far, it's about 1.5 feet. And so this planet will turn the opposite way, like if we're saying, hey, this is, theta is equal to 0, and at some other time this is going to be theta that way. This change in, well, I don't know. And I guess and this is a radius of 1. Oh, this is bizarre. But anyway, let's not do angles. But yes, this planet will rotate out a distance of 5 meters arc length. So the dog will move forward 0.5 meters arc length, and sorry, misspoke. The planet will rotate back 0.5 meters. So this is literally the equal and opposite. And I think when we talk about a planet just in space, I think it's actually easier to think about that, where you're just like, okay, I just have this chunk of mass just kind of floating in outer space, and then I have like something walking along it. The only way it can actually dig in its feet and then move, or you just can't have something for nothing. If it's bizarre because it's the conservation of momentum. Like if you start to move one way, something else has to move the other way, and we just don't experience that in our day-to-day life, because if we draw the Earth, one, it's an oblate spheroid. Even if we were on top, I don't know, just anywhere on Earth, it doesn't really matter. It's irrelative of the direction the Earth's spinning. Just pretend like the Earth is just stationary, but it's a huge chunk of mass. If you do the same thing with that dog and take a 0.5 meter step forward, and halfway during that step you're going 0.5 meters, and you're going 1 meter per second, you change your velocity from 0 meters to 1 meter per second. That's a change in velocity in 1 second, and then so that's an acceleration. Because you are a mass, F equals ma applies, and you have a mass of whatever you are, 70 kilograms times that acceleration of 1. You're going to apply a force of 70 newtons, which is divided by 4. It's about 20 pounds. So let's say 15 to 20 pounds. And hell yeah, that's kind of fascinating, because the faster you move, like if you're like a track star and you just push off the blocks, hey, you're generating maybe a larger force, kind of a bench press force maybe, and the Earth is you're going forward, your mass times acceleration. Or your mass times your change in velocity in that 1 second is going to be, in the 1 second, the Earth is going to rotate backwards. But it has so much mass everywhere on the perimeter, and then the mass at the center doesn't count, but all the mass on the perimeter. It only takes, you would have to take all the mass that's, you know what I mean? And so it's just all that mass is still moving, but it's only moving equivalent to your 70 kilograms times your 70 kilograms times your change in speed of 1 meter per second. So this number of 70, if you just as a number, this is momentum, mass times change in velocity. And we get that because F equals ma. We see that we're 70 kilograms. We changed our acceleration is just change in velocity per second. So I'm just saying, I just run problems for 1 second. So if you run the problem for 1 second, we have the force, the force times 1 second, Ft, is equal to the mass times the change in velocity in 1 second. You know, I mean, this is I think called impulse. Force times time, is that called impulse? Impulse is what changes mass. It's a mass changing velocity. Because it's really difficult to figure out the forces involved in like collisions, but if you can you know, because they happen over such a short amount of time. But anyway, so that's kind of my trick. Like, I'm not very good at impulse and momentum, but I always kind of come back to these simple problems. Is, hey, we have 70 kilograms. We changed our velocity by 1. This number 70 of us going forward has to equal the number 70 of the Earth going backwards. But guess what? The mass of the Earth, and let's make it ridiculous. Let's say all the mass of the Earth is on the exterior, just like right on the shell, just like our fake planet, and like it's not, and it's in a ring, in a 2D ring in the direction where we are. But we know that's not the case, so it's going to be an overestimate. And I honestly, this is where you use kind of like the factor of 10. Like, how would you guess? Because like rotating, like inertia, second moment of mass, you know, those are the things, like your I alpha, your you know, I omega something else. I don't know. Like this is what you're taking into consideration. You can't take a spherical Earth with mass in the center that doesn't count, and then mass at you know, progressively farther away circles, but also mass in the axis. Like if I'm walking this way on the Earth and I'm on the North Pole, you know, right down here on the equator, in perpendicular to the direction I'm walking, all this mass doesn't count either. Like the column of mass all the way through the Earth, while I'm moving this way and the Earth is spinning that way, technically, like those molecules aren't really moving. You know, they're rotating, but linear-wise, they're not like moving from here around a circle to here. All the mass in the center just kind of stays. I mean, it can rotate in position, but it doesn't count when it comes to change in momentum. But holy hell, I mean, you got 6 times 10 to the 24 kilograms of mass that if you put it in this scenario on the perimeter, then you would have to have a change in velocity. So this number times this number would have to equal 70. So this is going to be a hell of a tiny number. If this number was 1, this number would be, what, 6 times 10 to the negative 24? Is that how you do it? Sometimes I get confused with that qualifier. But man, so is 6 times 10 to the 2? Whoa, 6 times 10 to the 2. Sorry, oh, I'm messing this. 6 times 10 squared divided by 6 times 10 to the negative 2. Is that 1, or am I not writing it right? Yeah, why isn't that? Yeah. So it's got to be. Yeah. Oh, weird. Is it 6th invert? I don't know why I'm even playing around with this. Whoa. 6 times 10 to the 2 divided by 6 times 10 to the negative 2. Huh. But obviously that's no, that's not the same either. Oh, bizarre. Weird. I gotta do this. So we have 6 times 10 to the 2. Oh, that's right. I'm not dividing. I'm multiplying. Yeah, I'm multiplying by 6 times 10 to the negative 24. So sorry about that. So we have 6 times 10 to the 2 multiplied by 6 times 10 to the negative 2. And that's where I have to do this 6, invert the 6 also to the negative 1. All right, hell yeah. So yeah, whew. So it's so this velocity would be 1/6 times 10 to the negative 24 meters per second. It would be faster. If you're taking this step forward, this is going to be faster. And I don't know, on a later day, I really want to know with what factor is this going to be faster? Because, well, I think I know. Because a hoop A hoop has like an I, or a mass moment of inertia. Like it's kind of the thing that kind of calculates the mass, you know, as it's farthest away from the center, and this is mr squared for a hoop. Now a disk is going to be half that. So that totally explains it. If the Earth was a spinning disk, a 2D disk, and you were on top of it, excuse me, and then you took a step forward, I think from, you know, I can't even say, because this I term has to be related to angular speed, not just linear momentum. So this I term isn't related directly to linear momentum. It's related to like I alpha. It's angular momentum. So mr squared, omega mr squared, I omega is what I omega is angular momentum. I think that's right. And then I alpha is torque. Anyway, but in a 2D way, I mean, I don't know. I actually want to look that up. If the Earth was a 2D sphere and you took that step forward, the Earth would only go back 0.2. Well, in this case with the dog. So let's say we have the dog, you know, weighs 1 kilogram, and then this disc weighs 1 kilogram. When the dog goes forward, this disc goes backwards, actually double. So if this dog goes 0.5 meters, this disc has to go back farther at 1 meter. So it's to make up, so the linear momentum, because we don't have all the mass on the perimeter. We have a lot of mass in the center that doesn't count. So this has to, so the change in momentum here has to equal the change in momentum there. Oh, that was brutal. And so yes, you wouldn't have such a slow velocity, but this would be the slowest the Earth. You know the Earth, when you take a step forward, is at least moving back the other direction by this amount. So I think that's really fascinating. And Newtonian mechanics apply to all molecules. So if you're dealing with molecules that aren't like going hella fast, and in normal conditions, you know what I mean, atmospheric conditions, hell yeah. You are taking a step forward, and the Earth is rotating back at a speed of nothing. But it is a legit number that you can calculate. Alright, hell yeah. So that was brutal. And the whole point of that was to start drawing free body diagrams. So, and I guess, I don't know. How I do this is I'm going to draw block B. And I'm going to pretend like it's in outer space. Okay? And I'm going to put 100 Newton force on it. But then when we observe, you know, if we did the problem right, we observe that, well, we use F equals ma. If we don't have any other things going on, right, our acceleration is force divided by mass. So if it's just floating in outer space, and this is 7 kilograms, the acceleration would be 100 divided by 7. Alright, it would be 14.2 meters per second. It would change in velocity every second by 14.2 meters per second, which is fast. Free fall is just 10 meters per second, so it'd be going faster than free fall speed. Okay, so but we know that there's going to be a force this way. So instead of drawing it down there, let's just draw it right here. You know what I mean? Because we have a force of friction going that direction. So this is F. And if this force of friction was equivalent, if force of friction was 100 newtons, we wouldn't have any motion. So that's at least that. Why I pretend like this mass is in outer space is because if I identify even one force, like I have to start the process of finding other forces, finding all the forces, and if I don't find any other forces, I know that this is going to have motion. But if I observe that it doesn't have motion, and I know I applied this force because I have things like scales and, you know, I can figure out I'm applying that force, then it has to be the case. It has to be the case that there is a force this way of 100 newtons. It just has to be. Like, you need to figure out why. Like, some sort of mechanics is going on. We talked about friction being kind of like Velcro. But it just has to be the case. If you're literally applying a 100 Newton force to something and you see no motion, then there must be a 100 Newton force in the opposite direction. Just like, hey, look at this. Like, something that goes unidentified is that these blocks aren't going down. You know, their velocity is 0 in the downward direction. And we have an Earth down here, so why is that? Because we know that we have a force of gravity. And I would always write force of gravity as gravitational constant, the mass of this block, mass of the Earth, radius of the Earth squared, and then circle these three things and just know that those equal g of 10. You know what I mean? And 6.67 times 10 to the negative 11. This is 6 times 10 to the 24, and this is 6.37 times 10 to the 6. Just a lot of sixes. 6 times 10 to the 6, 7, you know, 666, you can think the devil, 6 times 10 to the 24, but all these, and then this is squared, so we have 10 squared goes to 10 to the 24, I'm sorry, no, 10 to the 6 squared goes to 10 to the 12, you add it to 10 to the 11, that's 10 to the 23, and then 10 to the 24 is on top. 10 to the 24 divided by 10 to the 3 is 10, because, hell yeah, you have a 6 here and a 6 there, and then you got 2 6s because you squared that. Anyway, I don't know why I like to go over that every time, but I think it's useful, and because there's just a chance that that might be the first time you've ever seen anyone's ever explained that to you. And this really gets into my motivation for making videos, because you get stuff like this equation, and I thought this was the Kepler equation. No, it's just Newton's law of gravitation. Newton's gravitational equation. But just no professor ever, like, hey, let's take 3 steps back and go over this. That every time that you see a problem where it says mg, or like weight is equal to mg, it literally comes from this equation. Like, you cannot deny this equation, because you might be doing this problem on the moon or Mars, or who cares. All right, so yes, if we have this force of gravity down and we know it's 7 times 10 or 70, but we visually see that there's no change in velocity this direction. It's stationary. There literally has to be a 70 Newton force upward. And so we just call this the normal force. And then just for terms, hey, force of friction always is a resultant of this compression of, you know, the weight and then the normal force. You know, it's kind of sandwiching maybe those Velcro, like elastic, you know, molecules together. And we say that the force of friction, even though the force of friction is in the, that's the other thing. This is going to be very helpful. So if I want to move this block, the force that I'm going to put on it is that way. The force of friction is always opposing movement. The force of friction says, hell no. You know what I mean? So the force of friction is always that way. In the last problem, I just didn't, and that makes sense, because the free body diagram, literally, any mass that you put in outer space and you put a force on it, it has to move that way, and it has to, if it's start with an initial velocity of 0, it has to change velocity every second by F equals ma, and the acceleration will be F divided by m. So whatever this force is, 100 newtons, and then you have a 10 kilogram mass, you're going to have an acceleration of 10 meters per second squared. It's going to be free fall speed. It's going to go from 0 in the first second. It's going to go 22 miles per hour, or 10 meters per second. Second, 45 miles per hour. And it's going to keep increasing in speed linearly forever. You know what I mean? And then I guess that's why I'm kind of interested. I think the first thing to get interested in is like Einstein's relativity. Like, what happens to things at the speed of light? But just any problem where you have acceleration and like you have it in like a space like atmosphere, like and and for whatever reason there's going to be a force on it forever, yeah, that's fascinating, because you're just constantly going to increase your... I know from like the floating head physics, to actually change your velocity requires F equals ma. So it requires a force. And a force, you know, is energy. You know what I mean? No doubt about it that force times distance is energy. It's the literal definition of energy. But the only way to actually get a mass to change its velocity is to put a force on it. And so just from my limited understanding is that anything that reaches the speed of light, the force or the energy, the force times the distance required to change its velocity any closer to the speed of light, just becomes an infinite amount of force. You would take an infinite amount of force to get that mass to go from just less than the speed of light to the speed of light. So, and hopefully I get that. Hopefully I have that right. That no particle... No, my brother, because I always like throw boneheaded questions off him. Or just kind of the basics. Be like, wait. Like, so there is no... I asked this because he's a quantum physicist. I was just like, wait, there's no mass... there's no molecule of mass that we can get to the speed of light. If a molecule of mass is not at the speed of light, and it's slower then that we have no way of accelerating it to the speed of light, because of... And I'm so glad that floating head physics guy is so excited all the time, because I learned some things, you know what I mean? And that's one of them. It's just like, oh yeah, it takes an infinite amount of energy to get that up to that. You know, I think I have that right. Anyway, so what the hell were we even talking about? Is that if we have this mass floating in space, we put a force on it. We want to reduce this, and so friction is just opposing. So if this is, and there's a lot of ways to visualize this. So if this is just outer space and there's no forces around, it's away from every star known to man. But then all of a sudden that we can just come in with like a bunch of, we can just like put a bunch of air molecules in its path. We're just going to have it go through just a brick of air molecules. And as it goes through those air molecules, those chunks of air molecules have to move and get out of the way. They used to all have no velocity, but because this thing went through them, it made other chunks of mass move. And so the only way to make other chunks of mass move is if this reduces its speed. You know what I mean? Conservation of mass and velocity. If this had a mass and velocity coming in, and it impacted a bunch of air molecules that have mass but no velocity, and then all of a sudden these molecules have to get the hell out of the way of this thing coming through, well, you must have moved those molecules. And I find this fascinating, because even from a Newtonian perspective, skydiving is exactly this. When you hit terminal velocity, the only thing that you're doing is moving friggin' air molecules from a velocity of 0 to a change in velocity. Whether they go back to 0 is irrelative. It goes back to the dog problem. It's just like we're just interested in this dog going from 0 velocity to its halfway through its step to its max velocity. That's the only part of the equation, only part of the question that we're trying to analyze. Because the second it goes the other direction, I can't even visualize that right now. I can just do one thing at a time. All right, booyah. So we did all that just to show that, hey, the force of friction is opposing motion. And this is going to come in real handy, because there's a lot of problems involving the force of friction, especially with springs. You'll have like a spring on a block, and then you'll have a frictional surface. And maybe this thing's oscillating. It's going this way, and then it's going back. And it's going back and forth, but it's really difficult to set up these equations, because just with a common 0 with an x-axis, you know, where this is the positive x, if you do this equation like in Excel, like every time you have a velocity that's in the negative direction, you know, that way, you have to say the force of friction is now opposing. But if this thing is getting sprung this way with motion and your velocity is positive, hell yeah, your force of friction is that way or in the negative direction. So that's the only bummer about like oscillating frictional problems, is if you're trying to just model them in Excel, which is a cool way to model them because you can just kind of take a fraction of you know, a very small chunk of time and then see how things are moving. Alright, sweet. So we have the free body diagram for this one. 7 kilogram block, we're going to have 100 newtons, and then we're going to have a frictional force back. If mu n, and we know the normal force, so we have a weight down of mg, that's going to be 70, and we have a normal force of 70 newtons. These have to be equal, and we know that mu n is the frictional force, and for static friction it's going to be half that. So we're going to have 0.5 times 70 newtons, so this is 0.5. That's going to be 35 newtons. So we can only pull up to 35 newtons, or 34.99 newtons, and this thing won't move at all. But that's weird because like all we're analyzing is block B on block A. If you only pull 34.9 newtons, hey, there's a frictionless, you're on an ice skating rink. So sure, block B won't move relative to block A, but the whole system will start to move very slowly forward. Cool. But the second you get more than 35 newtons, yeah, so that's kind of where the interesting part of this problem is. Because we kind of need to, maybe we need to analyze this static friction and its role going from static to kinetic. What happens that instant, you know, something goes from static to kinetic. All right, booyah. So, yeah, because this says 35 newtons, because the static friction is 35. 0.4 times 70 is, so 0.4 times 70 is 28. So we're going to have block B, 100 newtons, and we're either going to have a force of static friction of 35 newtons or a force of kinetic friction of 28 newtons. And I don't even know, like let's say you did have a force of static friction, well then you would have 100, then you would have 35 newtons acting on this 35. So you would have 35 kilograms. So F equals ma, acceleration is F divided by m. You would have the force of 35 newtons operating on 35 kilograms. And I think that's right. Yeah. And then your acceleration would be 1. That's not even an answer on here. So, and hopefully I'm just kind of totally missing something, but I don't think so. I think dragging this block across this surface means that kinetic friction is the only thing that's allowing this block to move. And it's weird because you got two different free body diagrams going on. We're saying, hey, block B is a force this way. The motion's going to be that way. We have a kinetic friction right here going that way. But then when we go to block A, okay, and again, I like to think of this as, hey, block A is in outer space. We can have no frictional components along here. But because these two surfaces are attached, it must equal and opposite. This frictional force is actually going this way. And I think that's where it's just like, I would like to spend a few days on just going over, like, yeah, the fact that this comes up in material mechanics a hell of a lot. It's, yeah, how would we, can we do this? I mean, let's say we have two chunks of heavy material that are very small, and we're going to put a force on this one, and we observe no motion. Velocity is 0. This is such a... oh, and then this thing is just rigidly attached to a table. Okay, so this is, from material mechanics perspective, well, you can make a cut anywhere. So we're going to cut both those chunks out of outer space, realize that we have a force this way. And if we put this system in outer space, well, we should see motion that way. But we go back to Earth and say, hey, we did this experiment and we don't. So there must be a force that direction. And the only place that you can see how there's no force out here in the open air, and there's even no force here and above this arrow. There's no forces around except this arrow right there. So when we do cut this, doing the free body diagram, cutting it out of outer space, the only place that you can have a force is on the cut that you made. So right here along this line is the only place that you can induce a force, and we see that there's a force right there. And this is what brings up, I'm not going to go into it today, just briefly, but hey, these forces aren't even in line, because that's the other thing. If you have this chunk in outer space and you're putting a force on it like this, but then you go back to Earth and you're like, well, it was connected to the ground, and we put a force on it, and we saw two different things. We saw no motion in this direction, no motion in this direction, and so we can put in the force of gravity, the weight, and then the normal force. So we can do that. Weight and normal force. Okay, we get that those cancel, but what about this one? Well, we say that we cut it right at the surface. We did our free body diagram, and so here is, I'm just going to call it the shear force V. So that's typically sometimes what you do. It's a shear force that way. Even the normal force at the ground, because we cut it right at the ground, hell yeah, we can see that there is a normal force. Else, this is kind of cool, because I take the, if you take the problem to the extreme, you have this that's connected to the Earth, and then hell yeah, the Earth is right there, and now you're saying you're putting a force there. But hey, the force of gravity between the center of mass of that and the center of the Earth, now that's irrelative. You know what I mean? To the actual problem, because the problem is this whole system. There is no weighted force. Is that true? I think that is true. I think the only reason that you get a weighted force is because you chop it out of outer space and make a free body diagram. Maybe not, but at least from this perspective, if we said this thing was attached to the ground and then we put it into outer space and then we apply these forces, they have to balance, and then this force has a shear force there, but this is what I was getting at. This is going to make it spin this way. And so we need forces to make it spin this way, or we put a moment in that direction. So these forces make it spin this way. So on the ground, if you push a pole on the ground, well, sure, it has to resist that force due to a shear force this way, and then if you actually take the ground, and then chop that out, well, the ground will see. This is where, yeah, just mechanically, the ground force sees that shear force in the opposite direction. And I thought I was going to come up with something magical, but it's just Newton's second law. It's just kind of fascinating. So, all right, hell yeah. So with that, let's bust out these free body diagrams. So we're going to have the normal force, the weight of B, the normal force of B, which is mu times, I'm sorry. Okay, so now we're applying this force of 100. Why did I draw it so sloppy? But we have a force of friction this way along the ground. And Oh, that's messing with me now too, because you are going to have a, I mean, this thing is not rotating, so you do have a frictional component that doesn't cause it to tip over. Yeah, that's interesting. I definitely am not going into that one right now. But yeah, you have things that are on a surface, and if you apply a force up here on them, hell, they might tip over, or they might just start sliding. I mean, you could imagine if you have like a wooden block, you know what I mean, and you push on it, hell yeah, it could just slide, or if the friction is hella, it could tip. And so, man, I'm not going into those problems right now. One problem at a time. But hell yeah, so this frictional force is going to oppose, and that's going to be equal to mu n. Alright, hell yeah. And then when we draw block A, sorry for drawing so sloppy, the frictional force has to be equal and opposite. Sweet. And the normal force has to be equal and opposite. You know what I mean? So we're going to have, I mean, you could just call this the normal at B. You know, because we opened up that surface. There's no difference between this and just one solid piece. The second you chop this into two chunks and make free body diagrams, you open up that layer. This layer can have a normal force, and like we said, if this force is off center, hell yeah, it's going to want to turn that way. So we also have a moment here that's going that way. But we're not going to, I really don't want to make mistakes on that. Okay, sweet. So we have this frictional force that way, and we have, and then we also have a weight of this, weight of A, and then we have a normal force of A, which is now weight of A plus the normal force of B. The normal force of the ground is going to see the weight of A plus the weight of B. Sweet. And the ground has no frictional force, so booyah. So this is the only driving force on this mass. And because it's a free body diagram, we've isolated it from that mass. And what's driving just this mass is this force. Cool. Because some problems, you know, especially like pulley problems, you know, maybe this mass is bigger. This is 100 kilograms, this is 50 kilograms. But because this one is, it's not in free fall, you know, this is resisting. This has a force of 50 times 10. This has a 500 Newton force resisting. This has a 1,000 Newton force going this way. So there's a net driving force of 500 Newtons. But guess what? It's driving the whole system. You know what I mean? Both masses are on the same rope, and it's almost like a linear system. So this problem, sorry for stuttering, I'm trying to get better. And we have a net force of 500 newtons, 100 kilograms, and 50 kilograms. So it's the same thing as these just combined, 150 with a 500 newton force. And then you can find the acceleration. F equals ma. Rearrange the equation for A, F over m. And you have 500, and let's do this one, because it's 500 newtons divided by 150 kilograms, and you get an acceleration of 3.3. This is a classic problem to do. Always do this one, get that 3.3, feel satisfied that you know what the hell's going on. Alright, so I like this problem because I'm also, because it's this problem isn't this. You know, when you have this driving force of 500 newtons, I make the mistake of being like, well, isn't that just being applied to this one? Or is it just, you know, but no, it's being applied to both. But in this problem, hopefully I have this right, this frictional force, after we separate it with free body diagrams, is only being applied to this A. And it's as if we develop a system where we say, instead of this block B with a force of 100, let's just have block A, and we figure out a way on its surface to generate a frictional force that's equal to whatever it was, 28 newtons. Cool. So if we're able to, you know, let's say we just blow, we have a backpack blower, and then we're just blowing air, you know, on it. And so if that generates, you know, and those air molecules are gripping into the rough surface and it's providing a frictional force of 28 newtons. Cool. And that's what's pushing A. It's irrelative of the motion of these particles. You know what I mean? You're just imparting a force, and then so that's kind of the interesting thing with this block B. And you have this frictional surface, and block B is no different than just air molecules going that way across a frictional surface. And as they do, they generate this frictional force on mass A. So when we find that force, we don't, and maybe I have this totally wrong, but I'm trying to explain my way into the reasoning why we say that F equals ma. We have mass A. We want to know the acceleration of A. And we know the force of A is that frictional force, which is mu times the normal force of B, which is mu times the weight of B, which is 28 newtons. So we say 28 newtons is equal to this 35 kilograms, and we just solve for A. Sometimes it's easier to do it this way. So A is 28 divided by 35, and we say A is 0.8. Let's see if one of the problems says 28 newtons is equal to both the masses combined, 35 plus 7. So 28 divided by 35 plus 7 is 0.666. And yeah, so that's not even an answer, so I feel comfortable. But yeah, that's almost the more interesting thing for me, especially when you're doing free body diagrams, to do this Newtonian thing of like equal and opposite forces. That's why we went over like the dog on the planet. If you're generating a force, it's only on, you know, the block that you're analyzing. And so that was kind of cool. And then we can analyze the acceleration. All right, holy hell. So again, we beat that one to death. And so we are done with this one. So this was a comment from a viewer. Hey, do a problem where you got two stacked blocks and figure out the frictional components. And it was kind of cool because I don't go into these with being like, oh, hell yeah, I got this down. And even if I did, that would not be the way I would want to. I would always want to learn new things. And so, yeah, we increased our fundamental knowledge. And so thanks for joining me. And guess what? That's a video.